Welcome to PyData. Great to be here. And we're gonna spend a bit of time looking at how to build a serverless machine learning system. I'm gonna just show you, if you want to take a quick photo of the slides. I know people like to go at their own speed. It's hard when we have many different people at different levels of experience. So I kind of let you jump ahead if you want, take a photo or look at the slides. You can get them directly from here. Okay, so we have 90 minutes. And please interrupt me whenever you want to say anything or ask a question. Just raise your hand, shout, I'll repeat the question. And what we're going to try and do is build what I call a minimal viable prediction service. That means build a machine learning system. So not just train a model, not just evaluate the model on some static data set, but actually build a system. And this work is based on a course that I've given. It's a free online course called Serverless ML. And we have a Discord community with over 1,000 members. So if you're interested in this, go out and check out the course. Go join the Discord. There's a lot of people doing projects there, getting help to build systems. There's a lot of cool stuff happening in the space. So we're going to build a serverless machine learning system. We're going to build it as 3 programs. So it's going to be 3 ML pipelines: a feature pipeline, a training pipeline, and an inference pipeline. And we're going to use some free online services. So the first one we're going to use is a platform called Hopsworks. It's an open source platform. It's a feature store, but also has a model registry in it. And that's going to store the state of our pipelines. We're going to use a service called Modal, which provides a very generous free tier to do compute. So that can run your feature pipelines, training pipelines, batch inference pipelines. And then as a kind of an exercise and homework, I'm going to run it from my laptop, but we're going to look at Streamlit as a user interface. Now, there are other user interfaces you could use, like Gradio and TyPy, but I've done this one in Streamlit. And I'm going to show you what we built before I get started. And I should give a little disclaimer. I've built a lot of these services, right? So I teach a course at KTH called Scalable Machine Learning. And last year, at the end of last year, at the beginning of this year, we had about 30 or 40 projects where students built full ML services in 2 weeks. And they did it with lots of different problem domains, everything from predicting sports scores to predicting air quality, as we had this example here. But anything, Bitcoin prices, sentiment on Twitter, anything where you can get data and scrape it from the internet. Because the main requirement of building a serverless machine learning system or something like this is that we do not have static data. So data has to keep coming. And I think every other machine learning course I've ever seen assumes you have a static data set, train on the static data set, keep some holdout data to evaluate your model, you're done. In the real world, you're not done. The data should keep coming. And if a model is not generating predictions the whole time, it's not generating new value. So this is the thing that I built, or I should say I built, I got help building. It's basically an air quality prediction service, and you can pick your city. I think I picked London here from the map. I think the map has the whole world. So what's interesting about air quality is that as a kind of a problem, there's tens of thousands of people have sensors on their balconies and in their gardens measuring air quality and making it available on the internet. But if you want to predict the air quality for your hometown or even your area or district in your city, there probably isn't a service there today, right? And as a prediction problem, it's pretty easy. All you need to do is store weather data for your area, get the historical air quality, and now you're predicting the air quality using the weather, because weather is a really good predictor for air quality. So if it's no wind, hot, and it's been hot for a period of time and there's been no wind, and there's a lot of cars around, it's probably going to be poor air quality. If it's windy, has been windy for a few days, it normally is good air quality. Unless you're on the wrong side of a major road and it's blowing the air towards where you live, then it might be poor air quality. So the features are things like, the wind direction, the air quality. You can have lagged features. How's the weather been the last few days? And then the great thing about weather is you get forecasts into the future, don't you? You get 2 weeks of weather forecasts. It's easy to get. Those are then the features which will help predict the air quality. So as a prediction problem, it's pretty straightforward to explain, I think. I just ran it here like 2 seconds ago to see, air quality prediction for London for the next 7 days. And it kind of looks like this. And we can see we've got the historical air quality all the way back. And it looks not too bad for the next few days compared to how it was in April. Okay, so that's basically a machine learning service. It's running it's actually running using GitHub Actions. It runs once a day, downloads the weather forecast for the next 2 weeks, downloads the historical air quality, measurements, writes them to this feature store, Hopsworks, and then we can retrain a model whenever we need to. Often we don't need to retrain it that often. And then the batch inference in this case, the inference in this case is not batch inference, it's online inference. So this is an app. It's running on Streamlit Cloud. You don't have to pay for it to run. And then when you press predict, it's basically getting the latest weather forecasts, and then it's making a prediction with the model on the air quality for your city. So that's the system we're going to build. And we're going to go through it. Now, we're going to have a bit of background as well. So I'm going to talk quite a bit as well, but feel free to jump ahead and create accounts on those services. The GitHub code is on my account. Do I have a reference to it? I'll just show it to you briefly. It's here, Jim Dowling and air_quality. So if you want to clone that, you can go ahead and clone that. You can run all this from your laptop, and that's how I'm going to do it today. I'm going to run these pipelines from my laptop. So it's Jim Dowling air quality is the GitHub repo if you want to clone that and get started straight away. So I'm going to talk a little bit about the background, and one thing about this is I think I personally am highly motivated by this area, why I think this is a really important area for data scientists, is that data scientists have been hired by large organizations in huge numbers the last few years, and they've been siloed into their own teams. And typically what happens is you get a dump of data from the data team, and then you train a model and you say, look, it would work really well in production. And you hand the model and the code over the wall to an ops team, and they say, God, no, I have no idea what to do here. How do I get the data? And it makes enterprises very inefficient in putting machine learning into production. And it means data scientists, all they do in terms of the workflow is get a dump of data, train a model, evaluate it, and hand it off. But the problem with that is that it's not. I don't think it'll be enough. You won't be able to survive as a data scientist in the next generation of machine learning if all you're doing is training models. Maybe there'll be a small number of people who do, but a lot of people will have to extend their skills to be able to build these feature pipelines and inference pipelines as well. And when you put those together, you end up with what we call a prediction service. So my claim is the following, that if you're just doing a course where you train model on static data and you evaluate the static data, you can do that in a company. You could take the annual financial reports and make a prediction for next year, and you could do the same again next year, and that could be your week, 3 weeks a year, you're doing it the same thing again and again. Well, why not just do it once? Write the pipelines once that take the financial reports and generate a prediction every year. Then you don't need to do it every year. You can basically write some pipelines, and it could be batch data. It could say, let's take all the financial data that's coming down for this year, create the features from it, train the model, make the predictions as a dashboard, and then make that program run again next year. And that's basically it. And that creates more business value than you doing the same work, every year for a few weeks. If you get to really high business value, so, we're looking at things like TikTok, which is, outcompeting the likes of YouTube, at least for my kids' generation. It's working with streaming data, so real-time data that's coming in. So in TikTok, if you're familiar with it, as you swipe through videos, they measure how long time you spend looking at each video. They classify the videos, and then that data gets updated in real time. So it's updated. They use Flink in the back end, and the model doesn't need to be retrained every 10 seconds. I think that's a very important point to make, right? It's not being more reactive by retraining them. It does retrain the model very frequently. They have a paper about it last year. They wrote about it, but you don't need to do that to make a system reactive. All you need to do is store as features. Well, what were the 5 most recent videos I looked at? How much time did I spend on them? What type of videos were they? With just that information, a model can make better recommendations than a static model that doesn't update the features that frequently. So I mentioned that I taught a course at KTH. This is a reference to it here. It's best you go through the slides to click on the link, but there's about 25 or 30 different prediction services that students built. And I think Charles, who teaches a course on deep learning at Berkeley, he basically said, well, back in 2017, you needed something like Michelangelo at Uber to build this. Now you can do it just as part of a student project in a couple of weeks. And we're going to do it in 90 minutes, not in a couple of weeks. So the machine learning system we'll build, and in general, any machine learning system you build with a feature store, the advantage of using a feature store is it can decompose a machine learning system into 3 parts. Right? There's basically 3 different components. The first component is that you have to take your raw data and turn it into features. So in the case of if we take weather data and air quality data, we need to go out to the internet. We need to have some API which will download our weather data. We need to download the air quality data. And we're going to have to then have that program run on at a certain cadence, at a schedule. So it needs to be scheduled to run. So it's not enough just, maybe you can do it in a notebook and schedule in GitHub Actions. And that's actually something I did in here. But you can also write a pure Python program and schedule it with a framework like Modal that we'll look at later. The second thing you need to do is then train a model with the features that you've created. And the model then needs to be stored somewhere. And the third part is then you need to make predictions. And those predictions can be batch programs that are run, on a cadence. Maybe once a day you update a dashboard. Last year I gave a talk here where I was predicting the height of waves at a beach in Ireland. So that would run once a day. Today we're doing an interactive system, which will basically, you'll go in, pick your city, and then we'll go to the feature store and pull out the data, the weather features in real time, and then make predictions from there. So the two components that you don't need to work on, in the infrastructure, is basically this layer at the bottom. So just to remind you, the feature pipelines will create features, write them to the feature store. We're going to work with pandas today. But you can see different technologies are often used for feature pipelines. You could have Spark if you have more data. You can have SQL, and you can have streaming even, like frameworks like Flink or Spark Streaming or Beam. Model training we'll do in Python. That's the I guess, de facto standard for doing model training pipelines. And then we're going to do an online inference pipeline. Today we're going to do it in Python. And I think what's really interesting for the Python community, and I mentioned this at the beginning, if you write Python, you can build the full end-to-end system with the user interface in Python. So you can generate not just a model, show your stakeholders, here's a model, here's the F1 score on the model. That's kind of interesting, but you have to explain then to stakeholders, what the hell is an F1 score and why is it important? Why don't you just show the stakeholders, here's the model running in the environment it'll be deployed in. Here's the model with a UI. Go ahead and click it. See the predictions it makes. Is it good? You can do that now in Python, and it's trivial to do user interface in Python. There's 3 frameworks I mentioned: Streamlit, Gradio, and there's another one I've forgotten the name of. But anyway, sorry, my brain's gone dead. TyPy, thank you. They're a sponsor here as well. Nice guys as well. But yeah, so you can write all that code in Python. You can build the whole thing in Python, which is great. And then you've got monitoring as well. We're going to do a little bit of monitoring in Python as well, but we're not going to go into that in too much detail today. Okay, let's look at these different pipelines. So I've mentioned this already, and this is just to remind you. Feature pipelines take data, produce features and labels if we're doing supervised machine learning. With features and labels, or targets, if you want to call them targets, you can get a model with a training pipeline. And then with the model and some features, you can get predictions. And that's basically your ML system, right? So a minimal viable prediction service is a way of developing machine learning systems where you get to your machine learning system as quickly as possible. So the first thing you should do, this is a basic principle we have in systems engineering. So any software engineering, you always try and get a minimal viable prototype in place. And with that, you can then expand it, make sure the thing keeps working. And then as you make changes, you're confident the thing keeps working. And unfortunately, that does mean testing. Right. So when we get into the likes of what we call ML ops, I'll talk a little bit about it later. You don't need to learn Docker and Kubernetes and cloud infra to do machine learning operations, but you will need to test your data, test your features, test your models. Because ultimately, when you make changes, you need to test them to make sure that the thing that you've changed, you have confidence that it will continue working. We also need to see that versioning is another core principle in ML ops. But the basic thing we want to do is get this minimal viable system working, and then we can progressively improve it. Now, we do that in data science already. We always establish a baseline, so some sort of baseline that we're going to show our model beats. But a minimal viable prediction service is that we want to build the whole thing with the pipelines, pulling the data from wherever it's going to come from, and with a minimal UI to show how the model will be used, whether it's batch or interactive. Okay, so I'm actually going to show a bit of code I'm going to show it all in notebooks, but I'll show you a little bit of Python as well. And the technologies I'm going to use, I'm not going to do the batch pipeline. There is one actually available, but we'll kind of skip over that. What you could do as an alternative is you could have air quality predictions made once a day and update on a web page. That would be nice, and it would probably be a bit faster than what I currently have, because what I currently have, you have to press some buttons and click and get to the air quality, and that's honestly annoying. But it's really, if you were to do this and have it for your city and make it available, I would run it as a batch pipeline that runs once a day. Probably if you want to do it for free, you can create PNGs and host them on GitHub pages, and it won't cost you anything. So you could run the whole system on free services. So I mentioned the service already. It's Modal. Training the notebook, I'm going to do it on my Jupyter notebook. You can do it in Colab if you want. And then I'm actually not going to use Hugging Face. I have used Hugging Face for this, but I'm going to use Streamlit Cloud. Okay. So there's a couple of concepts we'll need to know about. We're going to be using pandas to create our features. And when we write our features, we write them to something called a feature store. And we're using Hopsworks. It's an open source feature store. It's actually the first ever open source feature store. And it's also the only feature store available as a serverless service at the moment. So it doesn't cost anything to create an account. You get about 25 gigabytes of free storage, and it's unlimited. It won't time out, so you can build on it. So what we'll be doing is we'll be creating data frames as our features, so the weather data and the air quality data, and we'll write them to something called a feature group in Hopsworks. It's effectively a table, right? And that table is available for training, but also for inference. And one of the challenges in building machine learning systems is this synchronization between the training pipeline and the inference pipeline. You train a model, you need to get a batch of data to train your model with. Effectively, what you're doing when you're training a model is you're saying, give me a consistent snapshot of data with which to train my model with, which sounds easier than it is. We have issues related to data leakage in there. What if I'm pulling some data from one table, some for another one? If I get data leakage, how do I handle that? And then the other problem is then when you want to do batch inference or when you want to do online inference, you need to go back to this same platform and say, hey, give me yesterday's data. I'm going to make predictions with it, or give me the next 2 weeks of feature data for weather. I'm going to make air quality predictions with it. Or give me just one row of the current weather data for my city and give it to me within a few milliseconds. And that's a slightly different requirement than batch data. That's all very complex. So we have one abstraction to deal with that. It's called a feature view. And that's basically a selection of features. And with it, we can say, give me a snapshot of data for training, give me a snapshot of data for batch inference, or give me a row of data or a batch of rows of data for online inference. So those are the two abstractions we have there. But you can think of a feature group as basically a table of features, and a feature view as kind of in a database terms, a selection of features. There's no data. It just says these are the input features to my model, and I can use this and also the label. And I'm going to use this then to say create train data, but also to get inference data, batch inference or online inference data. Right. Now there's two APIs. When we did this originally, there's actually a more complex version on Hopsworks. There's a Hopsworks tutorial section, and the code is much longer. And I did a fork of it because I thought it was too challenging as an introductory project. So the original one used air quality data. There's free air quality data available at that API there. But it gives you tons of different air quality. So there's many different measurements of air quality. One is called PMI 2.5, which is the size of the particulates in the air. That one's very common, but there's other ones like PMI 10 and so on. So Free Weather API OpenMeteo actually added air quality, but only one measurement, PM 2.5. So in this example, we're going to take the air quality data from Free Weather API. So we don't need the air quality programmatic API. If you want to do a better job, then you should use that one. The good thing is that sometimes you have challenges with scraping data from these APIs because you need to register, get an API key, and then they rate limited and all that. This one is great. It's actually free and you can just use it. It is of course rate limited, but we haven't encountered too many problems with it, and you don't even need to register to use it. So let's look at the data model. I mentioned that the prediction problem is predicting air quality. And I said we have two sources of data. We have air quality data and we have weather data. So we have one table for the weather data. And we can see here that on the left-hand side in orange, we have the entity ID or primary key. That's effectively our city. So you can put in London as one of the cities we have there. And you can see then the second column, date or event time, is a timestamp of this measurement or observation that we've made. And we do that by basically going to the API and say, give me the weather for Dublin, right? And you can say, give it to me for the last 2 weeks. It'll give you the historical data, or give me the predictions for the next 2 weeks, and you'll get the predictions. And we can see there's the features that we think are important for air quality are things like wind, direction, speed, temperature. You get a lot more weather data like humidity and so on. It's not clear to me whether each feature has predictive power or not. I think you need to experiment a bit more to be an expert in this particular problem domain. But for educational purposes, these I think are the key features. Now, the way a feature store this is a table of data, right? This is like a pandas data frame. It looks like we've got date type, we've got types for the data. So we've got string as the city name, date time as the date. When we write it to a feature store and we read it out as a pandas data frame, we'll get back the same types. That's great. Sometimes we'll need to encode some of these features. So if I'm going to use XGBoost, I think in this case. So XGBoost, currently you have to encode categorical variables, but I think a new version will support unencoded categorical variables. But in the version I have, you need to encode your categorical variables. So strings will need to be encoded with something like label encoder, ordinal encoder, or one-hot encoder. And sometimes, depending on the model you choose, you may need to encode the numerical variable features as well. So we look at that as well as a challenge. And then finally, for air quality, as I mentioned in this particular problem, we're only going to look at PM 2.5 as the measurement of air quality. And we have a separate table here. So we're writing the features to an air quality table. And this is going to be a supervised machine learning problem. And this is the thing we're trying to predict, PM 2.5. But in terms of a feature store, this is just a column in a table like any other, because this could be an input feature to another model, right? So in this case, this happens to be our label. But in another model, maybe air quality is predicting, for example, the incidence of lung problems in a city over time. Okay, so let's get started. I gave you this link already. I'm sorry that took a little bit of time. This is basically what you need to do to get started. You need to clone this repo here. You need to install any Python version, I think between 3.7, 3.10. 3.11 won't work. So if you've got 3.11, create a virtual environment and install a different version of Python in it. And then there's a bunch of requirements to install. Some of them are related to visualization. There is one, we can have a look at them in a second. But basically there's a few of them to install. So take a photo of that. I'll leave it up for 2 more seconds. We'll take a photo of that if you haven't managed to type it down in time. And then I'll just show you what I've done for it. And shout out any questions if you have any questions at this point in time. Gabriel.
Talking about feature groups, it's a table and it's a feature group.
Yeah, so the question...
a feature group that goes into a specific model or a specific model.
Yeah, so the question is, what is a feature group? Is it just a table? And I didn't want to get into the details of it. It is a table. The reason why we call it a group is that sometimes we want this table to be available for batch calls. I want to say, give me a big batch of data. And sometimes you want to say, give me a row of data in 2 milliseconds. Right? And a data warehouse will not be able to support that. It won't be able to say, if I go to Snowflake and say, give me a row of data, it takes a second or two. So all feature stores that are currently used have 2 databases behind them. They have an offline store, we call it, which is a columnar database, and then you have an online store, which is a low latency database. So this table will actually, if you want to make it available online, you have interactive applications. They're going to say, give me some weather data in 3 milliseconds. The data will be replicated in 2 tables, one in an offline store and one in an online store. So one of the things that a feature store should do is hide that complexity from you. You don't need to copy the data to 2. You don't need to know about it. It's hidden behind the APIs. You just use the APIs, and then behind the scenes, all the magic happens. Okay. So embeddings. So yeah. So what kind of data types can you store in a feature store? Well, pretty much, at least in Hopsworks, most pandas data frame types are supported. If you have what is a vector or an embedding, it's basically an array of numbers, floating point numbers typically. So you can store those as well. Sure. Internally in the feature store, they may be stored in a different format, but when you read them back, they come back in the same format in Python. Okay, so this is basically all you need to do. You'll need to create an API key when you log in and sign up at Hopsworks. And let me show you what I did. I've done that already. And so that's not that one there. So this is not my cluster. This is my cluster here, I think. Let's have a quick refresh. Hopefully the internet will work here. I'm on the guest network. I guess most people are here on the guest network. Maybe I should use my phone. Right, let's close that. Okay, so while it's starting, I'm just going to show it. We'll start looking at the actual code. Let me don't show that. Okay, so this is when you've cloned the repo. This is what you'll get. You'll see that there's programs 1, 2, and 3. They're notebooks, and there are 3. Well, they're these two. The backfill we're using it to create the feature groups. So it's not going to be a production pipeline. We just need to run it once. The feature pipeline will be the program that we're going to run on a schedule. It's going to create the features, and then we'll have a training data set to train our model and register it, and then a feature pipe, and then we'll have this app is in fact our interactive application that's going to in this case Streamlit application. This is the user interface. Okay, so once you've registered in Hopsworks, you'll need to create a project. I've created one already. I called mine PyData originally, a very original name, and I ran the feature pipeline, and it basically created. You can see, got a weather and an air quality feature group. So these are the tables. You can see we've got a bunch of data there. If you're curious as to every time you run it, you get activity written in here. So we can see here that, I added 170,000 rows, 104 rows, and this thing as it runs, periodically, it'll just keep updating this table. So this table of features or feature group, it's a mutable thing, right? And this is really important because in data science, we often get static data sets. We're used to things like, oh, I'm going to encode my features. Now, this is a mutable table. It's going to keep getting updated. So you don't want to encode the features before you write them there. There's no point in taking a numerical feature here and normalizing it or standardizing it before you write it, because then the next time you write 100 rows, you need to renormalize all the data that's in there, right? And then you won't be able to do things like, oh, I want to go in and have a look at the data. We can preview it here. It's not really useful for EDA, so exploratory data analysis. You want to have a quick look and see what the weather looks like data. And this, by default, the feature store will compute statistics over your data. You can see some descriptive statistics, so the max wind, the mean gust speed, mean standard deviation, and so on. So basically, we're going to do the encoding in the training pipeline. So we're going to do feature encoding in the training pipeline, and we need to make sure those encodings are done consistently between training and inference. Right. So the way we'll do that today is with scikit-learn pipelines. There is also support in Hopsworks for doing it in a feature view declaratively, but we'll just stick with scikit-learn pipelines today. Any questions so far? And people getting started? Any issues or anything? You shout out, yeah.
Just to I think you wanted to. So we've got this separate source out there on the web.
Yep.
APIs.
Yeah.
And then the way that Hopsworks is used there is it's kind of like sort of caching some set of data. Is that right?
Yeah, so you can think of Hopsworks as being Dropbox for data, right? For your data is the easiest way to think of it. It's up on the internet, it's storing your data, and you don't need to worry about your data. And one way of thinking about it is files, right? So everyone messes around with CSV files, and you're storing them here, there, and everywhere. Now we don't have to worry about files anymore. The data is up there. We have a reference to it. It has a name. We have a project name. We have a feature group name. We have a version for that feature group, and then with that, I can just say, give me a data frame. You know.
And then basically you set up to say Hopsworks, I want data from this API.
Yeah.
Then Hopsworks itself will do the kind of once a day, just grab it.
No, so that's a great question. So we talked about this as a set of services, right? So let me go back and show the architecture at the beginning. So the 3 things that you need to write, or we need to write, are the ML pipelines: the feature pipeline, training pipeline, inference pipeline. So they're not running on Hopsworks. I'm going to run them on my laptop. I'm going to run them on Modal, and you can run them on GitHub Actions. Hopsworks does support compute, but not the free version. So the free version only stores the data. So it's the thing at the bottom. So in general, this is a general architecture. This is not specific to Hopsworks, but in general, you need compute to compute your features, to train your models, and to do inference. So you need to get them from somewhere. It could be, you're using AWS serverless functions for the feature engineering. You could be using Spark and Databricks. There's any compute engine that's out there you can use pretty much for feature engineering. Training is typically Python, so you could be using Azure ML, or you could be using, SageMaker, and that's totally fine. And Colab. So my students are all using Colab for most of this. Okay. So let's look at the first notebook. This is the backfill. So I'm just going to. Unfortunately, this doesn't look great. I'm zoomed in a bit, but let's have a quick look. So let me see if I can zoom out. Hopefully, you'll still be able to see it. All right, that's still visible. Yeah, great. We've got so many screens. I should be able to see from everywhere. So this is drawing a little map. So we need a library called Folium. You'll have to pip install that with the requirements. In the repo, I included a list of target cities. So you can add different cities in here. So whatever's available in the free open API. So when you clone the repo, you'll get this as a JSON file. This also means, however, that if you're running this on Colab, you'll need to download that file because Colab, unless you're checking out the code into Colab, then it won't work. So if you're using this in Colab, you'll need to download that file and put it in your Colab current working directory. There's also just some backfill data that's in here for the EU. That's in the GitHub repo as well. And we can have a quick look at it. This is just to basically fill up some data in here. Let's view the code. So that's this one here. You can see we've got some for different cities and different areas. So yeah, you can see it's basically we've got Amsterdam and somewhere down here we have London. If we go way down, I'm not sure where. It's typically before L. Now there's, you can easily add, if you live in London, there's so many different neighborhoods in London, of course. The data we have, I don't even know which area it is actually in London, but obviously the air quality varies massively over the city. So it'd be great to see like this done in many different neighborhoods all over the city, so you could compare one neighborhood to the other. And you can do really nice visualizations. We had somebody do this in Poland, doing all the major cities in Poland, which was looks really nice. Okay, so we can read up this data. In this case, this is just we're just filling up the feature store with some data related to air quality and weather, just so that we have some data in there. And yeah, it's not doing very much here, and it's backfilling the weather data as well. And we have 2 data frames at this point. There's a little bit of feature engineering going on here. So when we're casting the air quality date to a date time, nothing too major. Converting to a Unix timestamp, this Unix time. And then we basically end up with 2 data frames, right? So there's not really much feature engineering happening here. Just casting some data types to other types. We'll have 2 data frames, one with the weather data and one with the air quality data. And then basically at this point, if you run this on your laptop, it'll ask you to enter your API key. So you'll need to have created the API key in Hopsworks. And one thing I added in here, just that, if you're building these production pipelines, often what you'd like to do is you'd like to make sure that there's no errors, right, in your data. So sometimes if you're scraping data from the internet, you have a question? No. Okay. So if you're scraping data from the internet, sometimes there can be problems in the data. So the basic rule is garbage in, garbage out. And I'm using a framework called Great Expectations here. And actually I had a little error in this, I noticed earlier. And I think the error is that this particular rule, it interprets, you need to change the max value to be slightly higher than 0. I set it to 0 here, but you'll need to change it to be slightly above 0. And this expectation is just taking one of the columns. It's called the PM25. That's the measurement of air quality. And just validating that the measurement of that value is between, like in this case, I wrote 1 and 1000. Funnily enough, in some cities, and like Delhi and Beijing, they can go up to 1000, which is kind of crazy. Scary, to be honest. So we've got our 2 data frames, the weather and the air quality. I've added a data validation rule for the PM25. And then we're going to create this thing called a feature group. So this is my feature group here. So if you want to store a pandas data frame in this feature store, the only thing you really need to do to remember is to have a primary key. So you do need a primary key. Now the primary key in this case is city name. You can think of it as being the entity ID. This is the thing itself in there, because we also have an event time here, and we're using Unix time. So we've converted the date time to Unix time. And each row will be uniquely identified by the combination of the primary key and the event time. Okay? And event time is important because when we want to create training data later on, we'll be saying, oh, here's my observations of air quality in one table, and here's my weather data in another table, and I need to join them together at the correct time. I don't want to have the future weather coming in with an air quality. Then we'll have what we call data leakage. So what happens behind the hood is that the feature store, when you get training data, it will do this, what we call point-in-time correct join for you, so long as you've specified a column with the event time in your data frame that you're writing in. Now, if you don't specify a column with the event time, that's okay. If your data is static and never gets updated, you can do that and it'll work fine. But most of the time we'll see that data is, often in these types of problems, you have time series data because new data keeps coming in. We make predictions on the new data, therefore data has a timestamp associated with it. So once we've created this feature group, and I created it already, we then call insert, and I've added a little option to say don't wait for the data to sync at the back end. You just write to the platform and then the syncing happens with an ingestion job. So the way it technically works is it uploads to the platform and then the platform runs an ingestion job. The data stored is what we call Apache hoodie tables in a bucket at the back end. So that runs an ingestion job to update the data in hoodie. Hoodie is nice because it gives you some nice properties related to what we call time travel. We get commits of data, we get statistics around those commits, and then you can do things like say, show me the data as it looked like at a point in time in the past. So that's basically backfilling. Now the backfilling is something I'm running because I'm creating the feature groups and I'm using some historical data. But that's not the production job that I want to run, right? So I can probably just run this one because this one is, let's just restart the kernel. I just run it. It runs relatively quickly. Restart and run all. So this one is basically going to go to the internet and download some data. And so I do have to get the list of target cities I'm going to download the data for. So again, we're getting that from the GitHub repo. And then I put in the time, so the forecast time. So I'm looking for 7 days ahead, and then hindcast I'm going to download 10 days previous. Now you can change those numbers, and it'll download different amounts of data. And you can make that a parameter to this job. That would be a kind of smart thing to do, so that when you run this job, you can change that as a parameter. You don't have to go and edit the code itself. Now this is a notebook for for clarity purposes. So all it's doing is basically going to this API. We've got this API called get API data from OpenMeteo. And that's, if you go look for it, it's in this thing called functions here. So you can see there's a few functions that are coming here. So get air quality data. And then we have city code. And then we've got, so you can see we're getting the air quality data from a number of different places. And from OpenMeteo, you can see what it's doing here is it's getting the coordinates. We have some parameters that we pass in. This is the base URL where we're getting the data from, and then we're using the request API to download the data. And the data we get back as a JSON, we're converting it into a data frame. And you can see here the columns that we're interested in, and then we get back a data frame. So there's a little bit of code there to take our API request to get the weather data back and convert it into a data frame. And that's where most of the code is. Now, honestly, the way I like to do this right now is I like to open ChatGPT. And let's try it out because it's really good. I've never done this, so let's just see what happens. I do pay for GPT-4, which is good. So write a Python program to get data from the OpenAPI weather. Is it called OpenAPI weather API? Let's double write it down again. And for the city London, and return the results as a pandas data frame. So generally, it's pretty good at doing. So last year I gave a talk on predicting wave heights at a beach in Ireland, and it took me about a day to write that code. Because I was just scraping it from a website, right? But I asked ChatGPT to create it, and it did it. Actually worked. Okay, so it's going to probably the wrong Open Weather Map API. If we compare that to my one here, we're using a different one here. We're using OpenMeteo. Let's go look at this. So you can ask ChatGPT, say, please, can you use this one instead? You rewrite it and use this API instead. So you can see, it's not giving us a great answer, probably because it doesn't know enough about the APIs. But I'm pretty sure within a very small period of time, this is going to be much better. So you can see immediately it's at least pulling out longitude and latitude. You don't need to look that up. It doesn't understand much about the API. Oh, look, it does understand a bit. So it seems to be that it understands that these are some of the code. So this is pretty cool, and this will make your life much easier if you want to build an actual serverless service, because it's really good for this kind of activity. Right. I was looking through the feature pipeline. So we're getting back our data as a data frame, and you can see it ran here and it downloaded all the data. There's quite a lot, and I've got it back as a data frame. And yeah, so we can see here we've got the air quality data frame as well. So this is a slightly different air quality data frame. It's got the city name, the event time, and the PM 2.5. And the weather one looks slightly different. The weather one has a bunch more features than the air quality one. So the feature engineering that's happening here, there's not too much happening. We can see that, yeah, we're basically casting this to a date time, the date column to a date time. We're cleaning up some missing values, seeing if there is any missing values. And we're kind of done there. So that's our air quality that we got from the Open API, and we get the weather from this particular call here. You can see it, and it's downloading for a bunch of cities, and you can see it's run here. I ran it just there, and then we have some. Again, the feature engineering is very limited here. It's really just the data we're getting back is pretty good. We're just casting it to different types, and then we're going to write it to our two feature groups. So in this case, we've created the feature groups already, so we're just calling get or create. And we probably should just call get in this case, so it would make more sense. Because we'd like it to fail if the feature group hasn't been created, so you just call it get feature group. And then it logs into the platform, and then we upsert our data frames, and that one ran. And we can get, actually what's nice here is we also get the result of our grade expectations error. And I mentioned there was a problem in here in that the minimum value should be greater than 0. So it gave me a little error there. And then insert the other one. So that's kind of okay. I'm testing it out. This is how you would do development on your notebook, on your laptop, which is nice. But this isn't production, right? You hear this all the time from data engineers. Oh, this is these notebooks, data scientists, they don't know what they're doing. Right? If you just export this program as a Python, you can use nbconvert to export it as a Python program. We can then run it with an orchestrator. All right. So if you want to do the title of the talk is free serverless services, so we don't want to pay for it. So we're not going to use AWS serverless or something like that. So one option that you can do is that you can use GitHub Actions. So this is my GitHub repo here. You can see the code for it. So we have these things called actions. Probably a lot of you have seen. Everyone uses GitHub, I'm sure, or has used GitHub. And you've seen this button in the middle called actions. You have no idea what the hell it is, but it looks kind of nice. You'd like to have actions. Sounds good. Oh, I got an error. Great. Let's have a look. So I ran this morning. I didn't even look to see what the result was. But let's try and have a look and see what happened. So this particular GitHub action, you can see it ran. I got an error, but we'll figure out what the error is in a second. That GitHub action is defined in the code base. It's in this directory called .github workflows. So if you create a GitHub action, you always put it in this directory here. And if we look at it, we can just see what it does, right? It basically says run the code once per day at 2 p.m. That's what this first action does. It's going to run this every day at 2 p.m. It's going to take the latest version of Ubuntu. It's going to install Python 3.8. It's going to then do pip install my requirements.txt file. I can see what the error is here already. So it's going to take my Hopsworks API key, and then it will run the feature pipeline and will be run. Now, the reason why it's failing here, I'm pretty sure, is because I'm not using app.hopsworks.api. I'm using we have a newer release that I'm working on. So my cluster is actually here. And there's a couple of other environment variables that I need to set. So this one has a different URL and a different project name. So I need to set those as I should have set them here. So that's probably the error that I have. But let's have a look at see what the error is. So when the action runs, it just runs. By the way, they give you, I think, is it something like 3,500 hours? You get quite a lot, 350 hours. You get quite a lot of compute. And this thing ran in, it took quite a bit because it was pip installing a bit. But let's have a look at the output of it. Okay, so failure, test schedule. Okay, so you can see here, right, it failed at some point down here. Connection timeout, yeah, because it was trying to connect to app.hopsworks.ai, and I was actually, and I don't, there is no project with that name that I have access to. So it was a connection error. That's fine. So let's run it instead of GitHub Actions. Let's look at Modal. Now, Modal is this website here, and the code is in our repo. It's this one here, feature pipeline. I actually have some slides on this, so maybe we should look at the slides first before we go into the code. Let's look at the slides. So we looked at this already, and we looked at this. So for Modal, if you want to use Modal to schedule your pipelines, it's currently it has a very generous free tier. I've never been charged anything yet. I've been using it since like November last year, but they probably will start charging at some point. What you need to do if you want to run this example is you need to create an environment variable, and the Hopsworks API key is what you'll need to set. There are other, like I mentioned, there are a couple of other environment variables. If you're running Hopsworks on a different cluster, you would have a Hopsworks host or a Hopsworks project. But if you're running on the serverless platform, you only need to set the API key because it's hard coded the URL for that. Okay, we're going to skip. Yeah, Streamlit will skip. So that's what you need to do to get started with it. Let me talk a little bit about the pipeline, the one that we're doing here, so that we kind of put it in context before we look at Modal. So what we did, and we looked at first, was the static data. We had some static data in our GitHub repo, and we ran a backfill pipeline. That's kind of useful to get started, but it's not going to generate value. It's not going to, I won't be able to build a real system with that. And in this case, a real system is something that actually predicts the air quality for London for the next few days. You know, I can predict some historical value, and that's kind of interesting, but it's not creating real value. So our feature pipeline, in this case, it's doing incremental writes. So we're writing pandas data frames incrementally, and we're updating them in the feature store. Another way you could do it, if you wanted, real-time feed of air quality, you could write a streaming pipeline. And if you want to do that in Python, there's a nice framework called ByteWax. And if you're able to get access to, a live stream of air quality and, weather data, then that would be even better than what we're doing here. Because air quality is highly correlated with weather, but it doesn't really help you if there's a fire somewhere, right? So if there's a fire and that fire produces smoke with bad air quality, well then, a live streaming thing that's measuring the live air quality as it comes out and helps predict it would be even better. All right, so a little bit more on feature pipelines before we get into it. Like, I'm not doing too much feature engineering in this example, but the question often comes up is what should I do in my feature pipeline? Well, the kind of things that you typically do when you have some raw data coming in, and in the example of air quality, we do some grouped aggregations. So we'll show like the moving average of air quality over the last few days. That helps a lot as well as a feature. I'm not doing that one today, but it's in the Hopsworks tutorials repo. You can bin data. If you have categorical data, you can bin it, filter. Lagged features and rolling features are good. You can transform data with UDFs or pandas UDFs, streaming transformations, time series analysis, NLP, bunch of this stuff, clustering and dimensionality reduction, all that kind of stuff goes in feature pipelines. So any raw data you want to compress into a signal for your models for training or for inference, that's what you have in your feature pipeline. And sometimes you need to do large volumes of data. If you're doing it with pandas and it's too slow, you might need to go to Polars or Pandas 2.0. If it's too big for a single machine, you might need to go to PySpark. And I mentioned already, generally we don't do encoding of features in feature pipelines because it prevents the reuse of those features in models. And then we have a problem with write amplification. So when I want to write data and I need to re-encode an entire feature, then that is generally not a good thing. There are some cases where very low latency access to pre-computed features needed where you might need to do it, but it's not the common case. So this is what I mentioned, like what technology, should you pull out of your pocket to do your feature pipeline with? We're using Pandas 1.0 here, but if you're doing streaming, you might want to put ByteWax in there as well as another framework for streaming. But you can basically pick all of them. Now, this is the code we looked at already. How do we write a data frame to the feature store. In this case, we created a weather data frame and an air quality one. We created a feature group and we wrote it. So the air quality is pretty much the same. And the only difference here is that we had an expectation suite that we added. So that expectation suite, we can have a look at it in a second. It stores, you can see the results of your feature pipeline runs and see if there were problems in them. Now, the other thing I didn't cover, which I should cover, is in the notebook I was computing, it looked like I was computing all the features inline in the notebook. Sometimes that's okay, but it's generally bad software engineering practice. So good software engineering practice is to compute features in functions. So if I have a feature called air quality, and I want to compute the moving average of the air quality over 7 days, I could, put it all in line in my notebook, and that would be fine to get started with. But then how do I test this thing? How do I test this program that I've written? Even if I have a notebook as my feature pipeline, and I put all of the feature computations in a function, in a package. I've got a package called features, and then I have this module called air quality. If it's in a separate package with a module, I can write unit tests for it, right? Which is good. And unit tests will say, well, if somebody changes what the definition of the moving average feature is, maybe my unit test will warn me and say, hang on, you can't just change this because this will break all of the models that are dependent on it. So, and this is a simple one that's, it's computing moving average over 7 days, but if somebody went and changed it to maybe 14 days because they thought that would be better, maybe a lot of the existing models that are dependent on it assume 7 days. Or, if someone changes it to 3 days, that will definitely break the ones who are assuming 7 days. So a unit test in this case should warn you and say, hang on, this seems to be incorrect. So putting your feature functions in separate modules is useful for testing and reusability. The other reason why it's also useful is that sometimes we have features that it can only be computed on data that arrives at the at runtime. So if I've got an online model with an online interactive application, and I want to compute, let's say, the moving average of weather over the last 7 days, and I just get the observation for today, well, I can now call this same feature function. In this case, it's a Python UDF, but it can also be Pandas UDFs. If you need to scale, Pandas UDFs is the way to go. You can use them both in the Inference pipeline, and PySpark can scale them out really well nowadays. But that means that the same feature function can be used in both the Inference pipeline, the online Inference pipeline, and in the feature pipeline. And that ensures that there's no, if you go off and if a different team go off and implements your online Inference pipeline, they implement this feature differently, you'll have problems. You'll have what we call skew, online-offline skew. So I said I'd get to Modal. So let's have a look at how we turn this into a scheduled program in Modal. So Modal was developed by their team out of New York, a Swedish guy. I live in Stockholm. So this guy's ex-KTH as well. I'm not ex-KTH, he's ex. But he's ex-Spotify. And he basically had this idea that said, well, look, Kubernetes is nice, but it's not developer friendly. And, AWS service functions are okay, but they're not developer friendly. What he wants to do is basically get a Pythonic experience for running code in the cloud. And I think he's done really well out of this. I think this is the best kind of Pythonic way of developing pipelines, not just feature pipelines or data pipelines, also training pipelines, inference, batch inference pipelines. So we have basically the same code we had as before. The only thing you need to make changes to your code is firstly, he hates YAML files, and I think a lot of people can agree with that. Like YAML files lying around everywhere, what YAML files applied to the other. We had that with GitHub Actions. We saw we had a YAML file there. And the GitHub Actions also needed a shell script because, I could have run the program from there, but I ran the shell script as well because it was setting some environment variables for me. But it would be nicer to just have everything in a Python program, and I agree with that sentiment. So what we can see here on the first line is that you can create a name for your application, and then you can get an image. So in GitHub Actions, there's nice support for getting an operating system image. Here we're taking a Debian image, and we're installing a library. So in this case, we only need Hopsworks as a pip installable library. If you needed more, you'll add them to your list of libraries here. And then this code is a little bit messy because one thing they haven't supported yet is, hey, I want to run this code locally. I don't want to run it in Modal's cloud. Modal runs in the cloud, right? It's a container that runs in the cloud. But what if I want to run the same code locally on my laptop? So what I did was I basically defined a wrapper function called G, another one called F. I said, well, you know, if it's running in the cloud, run F for local and run G for remote. But if we're running just remote, you'll have just one function that you define. Here I've defined G, and I annotate it. I say basically use this image I defined earlier, schedule it to run once per day, and pull any API, any secrets I need from this name, this token. So in this case, our feature pipeline will need the Hopsworks API key, so I'll get it from there. You should never have, as you know, secrets in your source code. And this makes it really easy way to, you know, to basically extract that secret from their website and embed it in your program. So all our code will be in this function G, same code as we had before. So the last thing we need to do is call G. So you basically say, hey, I'm going to deploy this as an application on Modal and then run it. And this is the function I'm running, G. So they're the two parts. We have to define the program dependencies and the schedule of the program, the environment variables, and then we define a main to actually start the program scheduling. And GitHub Actions we've looked at already. You know, it's slightly, I guess the only advantage of GitHub Actions here is I'm scheduling a notebook. So if you want to keep running everything in notebooks, you can do that here as well. So let's look at Modal and we'll run it. Now, I said my one was slightly more complex. Because I want to be able to run it locally. You see, you've got local false set here. But if I set it to true, it'll just run the code on my laptop. So I think I've set to false. So let's run it here. You see, it gave me an error earlier because I wasn't connected to the internet. So let's just run it and we'll see what happens. I can talk our way through it. So when it starts, the first time you run it, it'll actually have to build a container. And that takes a little bit of time. But once it's built once, they cache them. So it basically downloads a container in, you know, less than a second. And now our feature pipeline's running. It's downloading all the weather data from the internet. And the nice thing about this is it's just like running it locally, isn't it? Like if I ran this locally, I'd get exactly the same output in real time. And now it's finished downloading all our weather data and our air quality data. It's run the data validation. It's uploading the rows to Hopsworks, and then it's done. So that's it, right? So that's me running it on my laptop. I've tested it. Not bad. Seems to work. Because I set up because I set it up as a stub, an application, it actually deployed it here. And I don't know why it's showing me some errors from earlier. I think I was running it on a different location, but you can run the same program. That program is now registered here at Modal. Let's have a look at our not logs. Okay, so you've got your deployed applications here, recently stopped ones. I think this is the one I just ran. Yeah. And then I've got these deployed ones here. Now, the secrets, you just go in here and you create a new secret. You can see I've got a bunch of secrets there. In this case, we're going to use the very bottom one, the custom one, which is an environment variable. So then you basically set that, you would type in here, Hopsworks API key, put in your values there, give it a name. So it's like PyData London. And now I can use this secret name PyData London in my code, and it shows you how to do it in your code. So you can just cut and paste that code from there. So now we've got a feature pipeline. It'll run on a schedule. It'll download our weather data, our air quality data, and it'll write it to the feature store. Any questions on that before I move on to training pipeline and the inference pipeline? Yes. Yeah.
Normally go forward and just get updated stuff.
Yeah, so just to repeat, so Modal is like a cron job that in the cloud that gets data from the APIs and writes it to Hopsworks. So now we've got data in effectively accessible as data frames in Hopsworks. So that's what it is, exactly. So it runs on a schedule. You don't need to worry about it unless you can set up things like alerts in Hopsworks and say if it failed, give me an email, write to a Slack channel, useful things, because that's kind of what data engineers do. Right, now we're expanding our skill set to what data engineers do, and there's no harm in that whatsoever. I think it really helps, expand your skill set to be able to run these things without needing to, talk to them. So you can talk to them anyway, of course. There's no problem in talking to them. But honestly, in the bigger level, there has been a trend. I don't know if everyone's noticed that everything is ML engineers now. It's like, oh, no one wants a data scientist. I want an ML engineer because they build stuff. Data scientists are useless, right? The problem has been that people have assumed that ML engineering is knowledge of Docker, knowledge of cloud infra, knowledge of all this stuff. I mean, you look at ML ops courses; they're all saying, "Oh, learn Docker, learn all this." You don't need to do. The problem has been that the infrastructure hasn't been good enough. So when the infrastructure is here, now you can see in Modal, I can generate a container just in a Python program and just set up my dependencies. I don't need. Okay, we do know there's problems with pip, and you should test that because your libraries can conflict and all that kind of stuff. But once this becomes easier, the challenges of running these pipelines becomes easier. Now the skill set comes back to, well, who can train the model better? Who knows the features? Who knows the domain better? Who knows the best techniques for doing it? And it won't be the ML engineers. Yeah. So I see a pendulum swinging back in as this technology gets rolled out more and more. Many of you who work in the enterprise will know that you haven't seen Modal in the enterprise yet. Well, it's not enterprise yet. Hopsworks is enterprise, on the other hand, but yeah,
bring in these orchestration tools and some data connectors, and then you don't have to worry about putting it on something else or getting orchestrated.
yeah. The question is, are we adding this capability to Hopsworks? So we have it already in Hopsworks, but I think we're talking about serverless, free serverless ML tools today. Hopsworks doesn't provide that as free compute. Free compute is expensive, right? That's one point. We're a European startup. We don't have any cash. Yeah, Modal are American finance VCs. They have cash. But joking aside, GitHub provide you free compute. There's a lot of people that provide you free compute. Free compute is expensive, right? So if you want to do free compute, you can do it that way. Honestly, I think people make too big a deal about orchestration. You can see that it's not as complicated in this use case as it could be. I think data engineering often do more complicated orchestration than what we're doing here. So the kind of things that you might do in data orchestration is you would say, okay, I've got a source data, it's creating another table, that creates other tables, which creates other tables. And you have this big, huge, what we call direct acyclic graph, which can fail at multiple points and you want to restart at multiple points. That's all airflow. I don't think we need to do all that for our machine learning feature pipelines. A lot of them are coming from data warehouses where we have these, what we call gold dimension tables from our data warehouse. They're already the feature, their data engineering have done their job. They've cleaned up the data. They've made it available there. So the pipelines we need to, update our features, because the features are not the same as what's in the data warehouse. We often typically have to, compress the data, aggregate it, all that kind of good stuff. And I think feature pipelines are not as complex as the kind of DAGs that data engineers work with. But that's my take on it. And it's also nice to be able to pick whatever technology that's out there. So last year at GitHub Actions I was looking at, and now Modal's better. I don't know what'll be better in a year's time. Any more questions? Okay, so we've done our feature pipeline. Cool. Let's do training pipeline now. And how do we get it? So I'm going to do a little bit of slides first because we have to introduce an abstraction before we do the training pipeline. We didn't look at Great Expectations. Let's have a quick look at that in Hopsworks. So I think air quality has some expectations in here. So you can see I ran this pipeline a bunch of times and we get some red is not good, obviously, and green is good. And you can basically have a quick look at, let's have a look at see the results. Oh, it's giving you JSON. You need to kind of read it. And this one gave me an error here. So saying, hey, you have to cast your data to the appropriate type. I ran out of time to do that. But, if it works fine, you'll be able to see if it didn't or not. Okay. Yep.
Understand the expectations, and I know you build that solution then.
Yeah. So let me explain how that integrates with Hopsworks then, because Great Expectations is run in our Python feature pipeline. So that code, the expectations are evaluated. If we're running it in Modal or some feature pipeline, a program out there, it's going to run the Great Expectations data validation rules there. So in the feature group, we can decide, we basically we say, I'm attaching this expectation rule, this data validation rule to the feature group. So when I write my data frame, it will evaluate it, but it's evaluating it in the feature pipeline. Then you can have a policy to say, well, if the data validation rule fails, don't write to the feature group, or just write and warn me. So that's just a policy you define. So that and this works also for PySpark. So the Great Expectations is not just Python; it's also PySpark. And what we get then in Hopsworks is we collect all the results of these feature pipeline runs so that you can just see how they went, right? Because that's kind of what you want to do. The whole idea of feature pipelines, it should run in the background autonomously, and you can just then get alerts if things go wrong, or look at historically how things went. This is unrelated to feature monitoring. I'm not going to talk too much about feature monitoring, but that's something we have coming out in the next release. This is where you can set up rules to say, for example, you can do there's a slight overlap between monitoring and data validation. So in Great Expectations, you can do things like, expect the mean value of the PM 2.5 within a batch to be, in this range. And if it's outside this range, give me an alert so your data doesn't get in there. But feature monitoring is often associated with models. So I got a model deployed. It's being trained on a training data set. And if we take any feature like PM 2.5 and we look at the mean value and standard deviation, we can say, well, when new inference requests come in with, and we get new historical measurements for PM 2.5, let's compare them to the mean and standard deviation in the training data set, because the model was trained on those values. What does it look like in recent time? And then you can basically say, oh, we have a statistical significantly difference between the two. And then you alert on that. And basically that's used to say your model is stale, effectively. We can see that there's been a change in the feature distribution that maybe means you need to retrain your model. It's slightly different to data validation. Right, so assuming we've got all these features in the feature store, we now need to go ahead and pick some features out of there to train our models with. And if you're at like Uber have a feature store called Michelangelo. They talk about it quite a lot. And we have a feature store summit, if you're curious. It runs in October. It's an online event. We've had 2 runs of it so far. But at Uber, you have like 20,000 features. So you have to browse and find the useful features. Often you can have redundant features, you can have irrelevant features. It's important to make sure you don't use prohibited features. And one of the issues that a feature store will help you with is feasibility of features. Can this feature be used in my online application, or can it only be used in batch? So this is one of the challenges that will help you solve. In our case, what we're going to do is we're going to join the features from the weather table and the air quality table together. And we're going to say, effectively what we're doing is feature selection. I'm saying, oh, give me this feature from here, this table, give me these features from that one. And I'm creating a feature view. And the idea behind a feature view is that this is the selection of features for my model. And they can come from many different tables. Now, if you're a data warehousing person, you can kind of think of this as being like a fact dimension model, data model this is something you can read up on. But effectively think of it as being, I have observations. These are the labels or targets that I have, and they have a timestamp associated with them. I'm going to pull in different features from different tables. And then when I want to create training data with this feature view, it'll make sure that this is all correct. There'll be no data leakage. But effectively, you can think of it as being starting at your label and the target that you're trying to predict, pulling in features from different tables. And that means joining. So if, for example, I'm doing air quality prediction for London, you can pretty much guess what the join key will need to be here. It's going to be London, right? So I'm going to say, give me the air quality where the city is London. Give me the weather data where the city is London. That's what we call the join key. And we'll pull it together. So you can see I'm joining on city, but we also need to join on date. We don't want to have weather data from a particular point in time and air quality from a different point in time. We need to make sure that they're matched up. So we're basically picking features in these different feature groups. So we're selecting the ones that we want to use. We're going to say what the target or label column is. It could be multiple columns, but in this case it's a single one. It's PM 2.5. We put in the city name, in this case London. And we're not going to do today, but you can also declaratively define transformations over features. You can say min-max scale this numerical feature, or label and code this categorical feature. And then what we get out of this is this thing called a feature view. And the feature view is metadata. There's no data being created here. It's just a selection of features that we're going to use for our model for both training and inference. Okay, and this is one of the hard problems, honestly, this is one of the reasons people haven't been building end-to-end ML systems and doing courses in it. It's actually a hard thing to do these things consistently between training and inference. But we think the feature view abstraction makes it a lot easier. So let's look at how we do that in code in Hopsworks. Firstly, we get reference to our two feature groups, air quality and weather. You can see that they're versioned and have names. So this is for ML ops. Versioning is important because maybe you have a pipeline running, and you want to train a new model with a new version of the weather data. So you go to version 2, but the old one needs to keep running while you're trying out the new version. So we got our two feature groups. Now we need to select the features from those feature groups. So we're only going to select PM 2.5 from our air quality feature group. We're going to select all the features from the weather feature group. So with the selection of features, we create this thing called the feature view, and we're just calling it air quality underscore FV. I don't like the underscore FV, but you can just call it air quality. And it contains both weather and air quality features, and it has a version as well. So that's basically the code that we need to use. We select the features that we need to use, and we create this feature view with that selection of features. And logically, this is what the feature view looks like now. So this table doesn't get created, it doesn't exist, but you can think of it as being, hey, I've got all these features. Maybe I've encoded some of them, like min-max scaled or ordinal encoder. I'm not going to do that in this example. The features have data types as well, and we can see the data comes in over time. Like there's because we have this event time column, we have this notion of data arriving over time. So remember, our feature groups keep running in the background. So maybe 2 months ago I created training data version 1, and since there more data has arrived, so now I'm going to create training data version 2 and train a new model and I have more data available. Maybe I'm going to make a prediction with the data that's available for the next week, and I'm going to make prediction for air quality at Delhi and New York. And maybe I have a live model running an interactive application, and it's going to say, give me the data for Portland right now. I need it back in a couple of milliseconds. So all these things is what we can do with our feature views, and it's going to create a consistent snapshot of data when it's training or when it's batch inference. So for batch inference, you might say, oh, the start time is this, the end time is this. For air quality, it's great. Sometimes you'll also say, hey, I want all the, give me batch inference data for all the users in my system. And that might mean give me the, the latest feature values for all my users. Spotify, everyone uses Spotify weekly. They do recommendations once a week. So what they do is once a week, they'll get all the features for all their users, all 200 million of them. And they'll make predictions about what they think songs they think you'll like, and then they write those to a big Cassandra cluster. And when you log in, it downloads the Spotify weekly predictions, and you see them in your app. Now, depending on the model that you train, you may have different types of encodings that you're going to use. So if it's a feed-forward neural network, you will probably need to normalize your numerical features so that you get a Gaussian distribution. Excuse me. I expect I'd be coughing a lot more than I have so far. Sorry, I have a little cough. Keep away, keep back. It's not COVID, don't worry. But the XGBoost, has different types of transformations. You'd need to encode. We're going to use that. We're going to encode categorical variables. We'll do it with scikit-learn. And then if you're using logistic regression, you need even different transformations. So this is how we did it in this example. What we want to do is we want to get training test data, and we can get it with time series split or with a random split. Now you can argue with weather about whether it's time series. The climate is changing. We know that, but weather is not climate. Weather is a short-term thing. So in this case, that's my justification why I'm doing a random split of the data here. But I think actually the serverless platform supports random splits today, but the latest version, which will be out in a couple of weeks, supports time series splits as well. Also, the code for time series splits is longer, wouldn't fit my slides. So this is cool, right? Now, this is where I claimed before, we don't need files anymore. So I can go to the feature store and say with my feature view object, give me a train test split. Everyone knows this is a common API you'll find in scikit-learn. 20% of my data will be my test set, 80% my training set, and I get back my data as we've got features in X-train are features in the training set, X-test are features in the test set, Y-train are labels in the training set, and Y-test are labels in the test set. So I want to encode my categorical variables, so I'm using a scikit-learn pipeline to do that. And then I want to train my model with XGBoost regression. So an XGBoost regressor model. So this is the pipeline that I'm creating in scikit-learn. This is me training the model with the features from the training set and the labels from the training set. So this CLF is now my trained model. And with CLF, so I'm getting my training and test set, I'm encoding my features, and then I'm training my model, and I'm doing the encoding in the same pipeline. So CLFit will do all of that in one go. So when I've got my model trained, I'm just saving it to a local directory with joblib. That'll encode it, and then I'm uploading it. Now, Hopsworks has a model registry, so we're using Hopsworks to upload it. This is the model has a schema, an input schema and an output schema, and we're just taking the same schema from our features. So this could be xtrain or xtest, it doesn't matter, and ytrain or ytest. We're going to take the pandas data frame schema, and we're going to say the model has the same schema. So that schema goes in here. We can also store metrics. So I don't show the code here for computing the accuracy of the model, but that we computed that slightly different with the test set. And then we have some sample rows that we added here, because in Hopsworks you can then try out a model as an endpoint, and you can just then get sample data, so you can click and say test the model, and then we save it. So that's basically what's happening here. We're serializing the model, we're establishing the schema for the model, and then we're packaging it up and loading it to the model registry. And again, think of this as Dropbox. It's just stored there. You can see it, and off you go. So let's have a look at the code for that. Actually, before I look at the code, let's look at it in the UI. So I have this feature view here called Air Quality FV. And if I click on it, we can see all of the features that are in here. So we can see here we've got, this is our target column or label. We've got a primary key, and then we've got the features here. I created 3 different training data sets. We can see them over time, and you can see statistics over them. We can also see the provenance, so the lineage of all of these. We had 2 different feature groups, version 1 and version 1 of air quality and weather. This is the feature view I created, and then I created training data sets using this feature view. So remember, the training data set is a consistent snapshot of data that I'm using to train a model with. And then the model got saved here, model registry. And this is my model, and you can see I've got actually a couple of different versions of it. So you can have, every time I run this training pipeline, it'll actually create a new version. So when I'm in my inference pipeline, I'll need to specify the version. I saved some metrics on the accuracy of it. If you click on Browse Model Files, I don't know if I saved an image here. Maybe I did. Let's have a look. Yeah, I saved this image as well. So if you save the image in the local directory, you'll upload it. So I can see, oh, this was the residual plot on my model's errors. So I get an idea of model training. Now, it's not those of you who've used the likes of Comet ML or Neptune or Weights and Biases. They're experiment tracking platforms. This is not an experiment tracking platform. So if you like to do experiment tracking, go ahead and use them. I mean, Weights and Biases, all of those 3 platforms I mentioned, and several other ones, they've really great free serverless tiers. I'm not covering them today because they're not operational services. They're really just about debugging and improving the quality of your experiments and your models. So you can use them in combo with what we're doing today. So let's look at our training pipeline here. So I have a couple of versions of it. So I'm going to, this one, let's have a look at this. This is one version of it here. Okay. So, basically when I start running it, it needs to log into the platform, get reference to our feature groups. Let's see if it's running here. Maybe I need to restart this one. This one is running in the cloud actually, but I have it on my laptop. I'll run the one on my laptop as well so that we can see it. I just want to show you something here because we've actually added something which is higher performance in here. I'll run this on my laptop as well, just so we'll go through both of them. Start and run all. Okay, so we talked about this. We get reference to our feature groups. We create this feature view by selecting features from the different feature groups. You can see here, hopefully you can see that. You can specify the join key, right? So the way Hopsworks works in the APIs for this is that if you have the same primary key in both of the feature groups, and then it will pick that. So the query optimizer will select that by default. But sometimes you have multi-part primary keys, and you might maybe want to specify the join keys as being, or even not part of the primary key, and you can do that. Okay, so we've got our feature view here. We create training data. We can see that runs here. So this runs much faster on the latest version. We're using Arrow Flight Service and DuckDB. The one that you're using here, version 3, is using something called Hive, so it's a bit slower. It'll take about a minute, I think, unfortunately, but now it takes about 3 seconds on DuckDB. So it's a lot nicer, a lot faster. Okay, and let's go through the code here. Sorry, we'll go from this one here. So we're going here. Yeah, that's reading all the data. I probably should have skipped that slide. So then, yeah, we're getting at our training and test sets. We define our sklearn pipeline, and then we have XGBoost regressor, and we define the pipeline. We fit it, and in this case, you can see that I'm actually casting the label and saying it's an int because it's a regression issue and regression. And you could have cast it earlier in the data frame, but I'm not sure if it was an int in the data frame. So one thing I skipped over in the slides was how do we compute the accuracy of our model? Well, we do have a test set here. So in this case, I'm computing mean squared error and R2 score. And what I can basically do with those, you know, I'm plotting then this image of them that I'm saving as a, I'm going to save as a PNG file. So we can plot the importance of the features as well. So when I want to upload my model, I can upload that PNG with it, so it's saved for the future. So that happens here at this point. You can see that I'm basically using joblib to dump my model, the serialized model, which is this CLF object, into this file. So it's a pickled Python file. And then the residual plot that I created earlier for evaluating the performance of the model, I'm just saving that to the same directory called model.dir. So when I save the model, then I basically say save model to model.dir, and anything that's in that directory, which is local on this on my laptop, will get uploaded there as well. And then this is the part where we actually create the model in the model registry in Hopsworks, and this is where it's uploaded. And that's basically it. If you keep running this, there's also some batch inference. You get an idea how the batch inference works. We'll basically get a batch of training data, or sorry, a batch of inference data, not in training data, and it'll make some predictions. And typically a batch inference pipeline will write the output somewhere, because maybe you want to generate a dashboard. Maybe we could generate a dashboard here and save it. I gave the example of GitHub Actions as a place you could save it to. But that's basically it. So that's the training pipeline. Any questions on that? We've got a couple of minutes left to do the inference pipeline. So let's do that. So this is our inference code here. And in fact, it's a Python program. So it's using a library called Streamlit. You can see we're using Streamlit Folium. So I guess for homework for you, if you want to have homework, you can deploy this on Streamlit. So I mentioned at the beginning, I probably wouldn't have time to do this all in Streamlit. But I don't remember if I said, maybe I didn't set my API key here. Let's see if we did. So the way Hopsworks works is that you need to set your API key. Oh, it is. I did set my API key, but you need to set them as environment variables, or you can enter them in, interactively. But typically, you would set it as yeah. So this should have opened something here. Let me see. Run it with the following command. Yeah, this is here. Okay. Am I running this on the right laptop? Okay, so it didn't print out the local URL. Normally it would just open a browser view straight off. But I'll just show it to you here because we had it running already. So this is one that's deployed on Streamlit Cloud. And what it does at the beginning is it just connects to the feature store, gets a reference to our feature view, downloads a batch of inference data. You can basically select the city that you want. It'll then download the model, and then it makes then we make predictions on that. So and you can make predictions over whatever number of days you want to make it. So this is what it's doing here. We got 7 days worth of predictions. So let's have a quick look through the code and see what's happening in here. So firstly, it prints out a fancy header. It's very important. Then we get a reference to our feature view. we get a batch of data from the feature store. You can see you can cache that as well. So, you know, if you're refreshing the page, it's often important not to rerun it. We download the model. So this is just going again to the feature store. We have the name of the model and the version. And then we're plotting these. So there's quite a bit in here, right? So this is using, you can see it's using some library, ST, which is it's Streamlit, to print out the chart. So we get this nice chart on the screen. And they're basically the functions. So basically we go in, we log in, we get our feature view, get a batch of inference data, download our model. We're using joblib to unserialize the model. And this pipeline, remember, it's not just going to run the model, it's also going to do the encoding of the categorical variables that we get back from the feature store. And then it's just printing out. So after this, it's basically all UI code. It's not too complex. We have a little submit button here. And it's making the predictions on the website. That's basically it. Now, it's not super, if you're a Python developer, this isn't too intimidating, in my opinion. It's pretty straightforward to take something like this and adapt it for your own UI. Yep, we're good. That's actually the last pipeline. That was our inference pipeline. So I just have a little bit more to cover before we're done. Any questions on the inference pipeline before I just talk a little bit about MLOps and then we're done? No? Okay, so this is what we looked at. We download the batch of data, download our model, we make predictions. That's batch inference. Online inference, slightly different. The main difference is this thing called get feature vector. Often in online programs, we want them to be interactive. We don't need to get a batch of data. We just want to get a row. For this user, we're making predictions. Give me this row back in 2 milliseconds, not in 200 milliseconds or 2000 milliseconds. Right, so let's finish by just talking about some of the principles. So once you've got your minimal viable prediction service up and running, you want to operate it. And this is what Google say is MLOps. I think it's kind of like, it's designed for consultants to sell stuff, not like for people to build stuff, because every box has some meaning, but every box, like you look at this and you're going like, I'm a data scientist, I'm not going to build this thing. What the hell is that? So the main principles, though, of MLOps is that this thing you build will change over time. The data that's available will change. The target you're trying to predict will change. You do have to automate testing of this, because if you make changes and deploy it and it breaks, that's not good. So you will have to add testing. And that means testing features and testing models. And tests should be run automatically. When you make changes to your code, run them. So you do need to learn PyTest at a minimum. I'm sorry, but you do. Put your feature functions in, put your features computation logic into functions. You can run them with PyTest. We saw data validation tests. You can have unit tests for your features. Models should be validated, particularly for bias. One thing in the feature store that's quite useful is we can filter when we get back our test data. So if I have, let's say, different genders, 3 different genders, I can get 3 different test data sets back. I filter by the 3 different genders. I evaluate the performance of my model on 3 different genders. And if it's similar, that's good. There's no bias. But if it's not similar, there may be bias against a gender. So model validation tests are important as well. I don't have time to go through them all. And then when you're deploying models over the network, we want A/B tests. The other thing for MLOps is versioning. So when you want to deploy a new version of a model, it might be connected to different versions of features. So the most important thing here is not just being able to upgrade, but being able to roll back, because problems do happen. So, you upgrade the model. We can see it goes to version 2 of air quality. We have a second version of our model using the air quality v2. Oh, we get a problem. We need to roll back. The pipeline should still be running for air quality v1. So it should just continue working. So often when you're making, changes to your code, you can often, when you've got testing, we talk about CI/CD, you go from development to staging to production. This is all good. You can read a link up that we wrote about how to do this. The same is true for model training. You do want to do development first before you go into production. And often that means evaluating your model on subsets or snapshots or what we call evaluation sets from your test set. And then finally, when you've deployed the models, you want to have A/B testing on them. So, at least in Hopsworks, we have support for a framework called Kserve. It's an open source model serving framework for Kubernetes. You can do red-green deployments where you deploy a model, it gets 10% of the traffic. You look at its performance, and if it's good enough, you can then deploy it to production. And then finally, when you're doing development, you'll have lineage. You'll be able to go from a problem in your model in production. You want to say, well, this was the model, this was the training data, this was the feature groups they came from, and this was the commit of data that came in. Because often you have to follow this to find out what was the actual source of a problem. And things like bias in models is typically data related, not algorithm related. I'm not going to say too much about, I mentioned we have versionings, but versions happen because, schemas changed or break. Maybe you've dropped a feature, you've changed the type of a feature, you've changed an embedding algorithm. That's when you need to change the version of a feature group, for example. So I'm going to finish with just I'm just ahead of time. With an idea here. Look, what would the ML service you're going to build? So one idea I don't have time for, I'd love to do, would be something like personalized GPT-4, right? We had a quick look at it. It has a great model of the world, but doesn't have any model of me. But if I write feature pipelines that create models of me, then I can go to the feature store and say, what did Jim do yesterday? What did he do last week? How much money has he got in his bank account? I can use all that to create a prompt to say, oh, what should I do in London? I say, you've no cash. Go to the British Museum, it's free. Okay. So with that, I'll finish up. If you're interested in this, think it's kind of an interesting area, go to Serverless ML, have a look at the course, join the Discord, give us a star if you like it, and thanks, and enjoy the rest of the conference.